Nice to meet you all. Thank you for coming. I'll give you a slightly different perspective on that talent question that was here. We're causaLens, and we believe in automation of the repetitive data science tasks that one does, so that we can go to the next level of abstraction and do even more exciting things. So rather than thinking about how can we optimize this parameter, how can we clean this data set, how can we decide which architecture of deep neural networks to use, if we have the ability to automate that, we can do more interesting things. And so the interesting thing I'll talk to you about today is how we can, if we have managed to automate this process end to end, from data cleaning to figuring out what model makes sense, then we can start searching for data autonomously. We could start saying, if I have this portfolio, what data set out there could help me improve the performance? If we are an air cargo carrier, we could start answering the question, what data set out there can help me predict more accurately how many planes I'll need in 3 months' time? If we're a pub, we could just say, how many beers will I be selling tonight? So you order the right number of beers. So if we automate this process of discovering signals, and by signals we mean something that helps us predict the future, we can start opening up new possibilities that we couldn't imagine previously. And so the talk will be about the process of doing this. It's very hard, and it requires years of research and a lot of brains to be able to automate it. So causaLens is a deep tech company, one of the fastest growing in Europe, and we're hiring activists, so don't be shy. Just come to our website. So now we'll go back to finance, and I have some typical plots here. Now on this side here, what you'll see is two signals that have a correlation of 85%. What that means is that when one thing moves, the other moves kind of in the same direction 85% of the time. So now I would like to run a little signal auction. So imagine that the blue signal is the S&P, and the yellow, the orange signal is something that lets you predict the S&P 85% of the time. How much would you pay for such a signal? So who here would give me $1,000? No. Who would give me, I don't know, $500,000? Oh, you give me $500,000.
If you could predict it 85% of the time.
85% of the time, yeah. And well, that would be great, because I managed to do that with 2 lines of Python code this morning. And so I would be making, my revenue would be, my revenue margin would be 100% almost. And so this is just a clear illustration of one of the most common problems in finance, that correlation doesn't imply causation. And by the way, these two signals have been properly stationarized, and all these other things that can go wrong. It's only even after that they still demonstrate this high correlation, but it's purely by chance. And so that's a major problem. And in fact, if you do this at scale, if you're trying to search for signals at scale, what you will find is that you'll find a lot of these spurious correlations, but you can't really do much with them, because they're just related to the past and not to the future. Then we ask our question, the other question on the other side of the spectrum: do low correlations matter then? Well, the answer is everything in finance is correlated very low to the thing you're trying to predict. No matter whether it's one asset or a portfolio, no matter what you try, you'll get a very, very small signal. So the noise is so huge, and the signal is kind of buried in the noise. Most of the things in finance will give you very, very low correlation. So that means we have 2 problems, well, more, but so far 2 problems. We have high correlations that don't matter, and we have low correlations that matter. And most things are in between the two. So we have no good way of figuring out what we should use in our training strategies. And then, of course, we have the problem of overfitting. So even when we feel we found something that matters, we build a back test and we do all the metrics. We humans, we like to take a look slightly in the future, see what the holdout data set is, and we like to repeat the experiment many times. So we get into this problem of overfitting, and humans are great at that. And all in all, we get to a world where we are trying to predict the future, but we're looking backwards. We're looking at backward-looking correlations that may matter, may not matter. We're really driving forward by looking at the rear view mirror. And that image, I think, summarizes most of the market participants right now. So for us, it's not a surprise that a very large number of active asset managers are underperforming their benchmarks. Then some more problems. So I'm going to give you loads of problems, and then we'll get to the solution. But when people talk about data, they tend to oversimplify things. This plot in blue there is the original data set. But actually, with manipulations of that data set, you can derive infinite number of other data sets. And so where do you stop? We have the average yield of Germany, then we take the 4-step lag, we get a new time series, and then we take the exponential weighted moving average over 6 steps, we get another time series, and then we take the exponentially weighted z-score, and we get another time series, and so on. And in fact, theoretically, there's infinite number of derived data sets you can come up with. Now, this is for one signal. We have billions. In fact, we have one of our partners gave us access to 3.7 billion of these things in blue. And you can, I guess, work out the exponential derived number of series. So really the problem is which one of those, not just raw time series, but which ones of all these derived time series help me predict the thing that I care about. And of course, data doesn't come clean like this. It comes with gaps, and it comes in different frequencies. So one is published weekly, the other is daily. And so then you have infinite ways to decide how to align them, infinite ways to figure out how to fill the gaps. And of course, you can't have forward-looking bias when you do that. So it's pretty tough. So here this summarizes the problems we outlined. So we can make wrong conclusions because of low correlations. We can make wrong conclusions because of high correlations. We have infinite number of things we can derive from our original data. Overfitting is very easy to do in a low signal to noise world. And if we don't use the right techniques, we may not capture some of the nonlinear behaviors that are happening. So those are the problems when one wants to figure out signals at scale automatically. You have to solve all these problems. And so here is just one little flavor of how real data looks like. Real data comes in all sorts of formats. So these are 3 vendors supplying sentiment indicators. And all 3 vendors have a different way of supplying the data to you. So this vendor has 2 files, one for Google, one for Apple, and this other vendor has Apple and Google in one file, and this third vendor has them in a slightly different way. And so one needs to solve this problem, essentially bring all this data into a normalized, clean format to be able to even start doing signal testing. And then, of course, if you do it at scale, this problem just explodes. So now you have billions of files in different formats that you're trying to address. And that's kind of where we are now. People take these random formats and they write some scripts, Python, MATLAB, whatever it is. And then they go and they're like, okay, finally I cleaned my data. I spent then 80% of my allocated budget on that. And now I have to go and actually try to find some signals here. And this process is very, very painful and lasts for a very long time. So some of our clients spend months or weeks or years, depends, to to go from this raw data to figure out the optimal model so they can prove whether the data is valuable or not. So a typical run through this would cost like 30,000 pounds just to try one experiment in data science time. And of course we saw that because there's so many infinite ways to do it, the cost is also infinite if you really wanted to try everything. Just for one experiment with very simple data, the one we saw, this is the total number of models one could build in principle. And so needless to say that we don't have that many data scientists to be able to try them all. And so that's where automation comes in. If we had a way to automatically clean data, if we had a way to automatically discover signals in data, if we had the ability to automatically figure out what are the best algorithms and parameters, and we managed to have, to synthesize this in one line of code, then we can build products on top that allow us to do this at scale and search for valuable data and scale. And it also allows us to solve another problem, that is when a human builds a model, the model is set in stone. That's, you build it this year, and then for the next few years, the model is in production, and the performance goes down, and that's kind of what people refer to when they say model drift or alpha decay. But if you have it automated, you could repeat this process every day, and you can ensure that your model remains performing as the world is changing. So just wanted to bring in this. The world thinks that there is talent shortage for AI, and when they say this, they refer to the traditional way of building models. But actually we say, why not empower everybody to use a technology that automates this process and short-circuit their training, so we can all do things that matter for our organizations, no matter whether it's asset management or food wastage, or saving the planet and improving how we consume energy, or whatever would benefit from actually in the future. So yes, there is a huge talent shortage on the traditional data science workflows, but I would argue that it's better if we focus our energy and efforts on using automated processes and kind of move up in the value chain. And then of course, when you do this for real at scale, you incur a lot of technical debt. So this is a paper from Google. It's titled Machine Learning, the High Interest Rate Cost of Technical Debt. And what they're trying to say there in the paper, in summary, is that it's dangerous to think of machine learning as a panacea that will solve everything. Because when you try to do that scale, you're actually incurring a lot of technical debt. And it's really, really hard to do it at scale. It's very easy to have one model in production, but having billions that are connected to each other and kind of seamlessly running in production is very tough. And it's really like a credit card with high interest rate. So I think automation can help us there as well. So just to summarize, we talked about this notion of automatically discovering signals through the lens of predictive models and solving all the problems that we illustrated. And this is how it would look like. So, and that's actually how it looks like in our technology. You can just say this, and you've just saved £30,000 and 6 months of human time. And just if you think I'm exaggerating things, I would like to show you that this is real. So this is the CEO of Allianz Global Investors. It's a very large fund. We were invited to participate in a competition where there was 141 companies. Many of us were at a much later, many of the companies were at a much later stage than us. And we had a very simple instruction. Here's loads of data. Figure out how to predict these 20 asset classes in the future. Submit those predictions, and we will test them, on data you have never seen. And so we had 48 hours, a big clock, it was ticking, and we were all there, braced for 48 hours of no sleep, loads of coffee. We plugged in our machine, and in those 48 hours we were able to test autonomously 100,000 signals, and we're able to build 11,200 models. And when we submitted the out-of-sample predictions, we won the competition. And so you can read kind of the comment of the CEO of Allianz is that it was the only approach that they felt would scale in the new world. The rest of the teams were only able to explore one predictive model and just a handful of potential signals. So, what's very interesting though is that on the back testing, we were the worst in terms of performance, but on the unseen data we were the best. So that just goes to show how easy it is to actually overfit on data that is low in noise. And if you use our technology, this is kind of what you get. You say, hey, here's a lot of data, billions of time series. I want to find what predicts the thing that I care about. You launch the line of code or that button, and you get a signal back tested. But anyway, I don't want to talk too much about technology. I just wanted to inspire you that we can do things in a more efficient way, and we can focus our human energy on doing things with this sort of technology. And this is just a very brief intro on us. We are London-based, rapidly growing. We are looking forward to welcome 50 PhDs in the next 12 months. We've won loads of awards, we're happy to have any one of you that would like to join the next generation of data science. Thank you so much for listening, and if you have any questions, I'll be delighted to answer.
Any questions for Darko? Oh, there's some.
Oh, yeah.
Hi, so my name is Philip and I work as a quant and an asset manager. So is basically your platform like a way to build like machine learning pipelines and kind of automate all the pipeline building, so then you can test all the models more quickly on top. So if everything's like streamlined, you can just test all the models more easily. So what's like the secret sauce in that sense? Is like the pipelines or the...
Sure. So we operate on a much higher level of abstraction. We build data science agents that are able to develop intuition around what to try, as opposed to go for a brute force approach and trying out all possibilities and have a very computation intensive with high probability of overfitting. We train our virtual data scientists or agents on proprietary data that we generate, and they've observed problems similar to the ones you're trying to solve. And therefore, when they come and look at your problem, they say they develop some intuition already, and they know what to do next. Yeah. So the way we train our agents has an aspect of reinforcement learning, but it has other ingredients there as well. Any other questions? Yeah.
My name is Victor. I'm a student at UCL. I was wondering, so after that competition, did Allianz actually implement it, and what were the results? Just so we had a panel before, and they seemed quite, there was an asset manager that seemed quite skeptical about applying it to this front office actual.
So I can't talk about any particulars of our individual clients, but what I can say is that the best of the best hedge funds and asset managers have us in production, not only in the front office, but kind of everywhere. They use us in a way to decide what data sets to buy. They use us as a way to empower their researchers. They use us actually on the process side of things to trade fully systematically. So we only deal with front office type of use cases. So I would say this is it works, and it's the most forward-looking funds and asset managers already use us.
Since you mentioned the problem of basically that you can generate infinite data, do you use a generative approach that you sort of tweak by incorporating additional data that
question. So our agents are trained on both artificially generated data and real data, and a blend of the two. So we use GANs and generative approaches and many other approaches too. So we're quite keen on this topic. A lot of the exciting stuff we haven't published yet, but yes, GANs would be kind of a, let's say, baseline type of starting point. Yeah.
Thank you. Sorry, I didn't introduce myself. PhD at Imperial College.
Oh, nice. Yeah, excellent. Any other questions?
All right.
Great. Thank you so
Thanks
much,
again.
guys.